Your computer is off, the screen is black, the fans are silent, the operating system doesn't exist yet. Your files, your passwords, your browser tabs, your work, none of it is awake. And yet, something is already running. Before Windows, before macOS, before Linux even gets a chance to breathe. There is a tiny chip on your motherboard that wakes up first. It decides whether your computer is allowed to start at all. It decides which hardware is trusted, which software is real, which instructions are obeyed. You never log into it. You never see its interface. Most people don't even know its name, but it has more authority than the operating system you argue with every day. If this chip says no, nothing else matters. Not your SSD, not your CPU, not your expensive GPU. And here's the uncomfortable part. This chip doesn't work for you. It works before you. And once you understand what it does, how little code it runs, and how much power it holds, your computer will never feel like it fully belongs to you again. Early PCs had no opinions. You pressed the power button, electricity flowed, and the machine did what it was told. If a piece of software claimed it belonged there, the computer believed it. Viruses were rare. Malware was clumsy. The idea that your own machine might actively protect itself from you sounded paranoid. Then computers became valuable. They started holding money, then identities, then entire companies, then governments. By the early 2000s, attackers weren't just teenagers showing off. They were organized, funded, patient, and they discovered something awkward. You don't need to break the operating system if you can sneak in before it loads. That's where things got messy. Hackers began targeting the boot process itself. Tiny pieces of code inserted so early that antivirus software never saw them. Rootkits that survived reinstalls. Malware that lived comfortably beneath the OS, watching everything quietly. You could wipe the drive, reinstall from scratch, and the infection would smile and stay put. Manufacturers panicked, quietly. They needed a way for the computer to recognize itself, to know, with mathematical certainty, whether it was starting in a clean state, not by vibes, by cryptography. So they added a chip, physically separate, small, boring-looking, almost invisible on the board. Its job was simple in theory. Store secrets that software can't easily touch, measure the system as it boots, create a chain of trust. If something changes, firmware, bootloader, kernel, it notices. This chip got a friendly name, Trusted Platform Module, TPM for short. But don't let the name fool you. It wasn't built to trust you. It was built to decide whether you can be trusted. Over time, it became standard, first in business laptops, then servers, then almost everything. By the time Windows 11 rolled around, it wasn't optional anymore. No TPM, no install, end of discussion. And that's when regular users finally noticed it. A chip they never asked for. A requirement they didn't understand. A gatekeeper that suddenly mattered. Because this tiny chip isn't just checking for hackers, it's enforcing rules. Rules written by manufacturers, platform owners, and standards committees. Rules that decide what allowed means. And once rules exist at that level, they're very hard to argue with. That's where the story stops being abstract and starts getting personal. You press the power button. That's the last time you're in charge for a while. Electricity reaches the motherboard, the CPU resets, and before your operating system even exists, the firmware takes over. Not Windows, not macOS, firmware. Code burned into the board itself, and standing quietly beside it is the tiny chip. The firmware starts making promises. It says, I am the real firmware. I haven't been modified. The chip doesn't take its word for it. It asks for proof, cryptographic proof, measurements, hashes, numbers that change if even one byte is different. Those measurements get sealed inside the chip. Then the next piece of code loads. The bootloader, same process. Measured, recorded, compared against what's expected. This continues step by step. Firmware to bootloader, bootloader to kernel, kernel to drivers. A chain. Break one link and the chip remembers. This is called a chain of trust, but it's really a chain of consequences. If everything matches, the system proceeds normally. If something is off, the computer can warn you, restrict features, or refuse to boot entirely. And here's the key detail. The operating system doesn't get to vote on this. By the time it's running, the decisions are already made. Now add another layer. That same chip can generate encryption keys that never leave it. Not to the CPU, not to memory, not to software, ever. Programs can ask the chip to use a key, but they can't steal it. This is how disk encryption works without you typing your password every time. The chip checks that the system booted correctly, then quietly unlocks the drive. Convenient, elegant, slightly terrifying, because the math is unforgiving. Change the firmware, key stays locked. Swap the motherboard, key stays locked. Boot a different OS, key stays locked. Your data is still there, perfectly intact, and completely inaccessible. This is where hype meets reality. The marketing says, security, protection, peace of mind. What it really means is dependency. Your files are no longer protected by what you know. They're protected by what the machine recognizes. And recognition is strict. This chip doesn't understand intent. It doesn't care why something changed. It only knows whether it matches the approved pattern. For corporations, that's a dream. For individuals, it's a trade. Because once security is automated at this level, control shifts from users to policies, from choices to compliance. And most people don't notice until something goes wrong. That's when the tiny chip stops being invisible and starts being the most important component in the room. This chip doesn't just verify reality, it defines it. For years, this all lived in the background. Corporate laptops, government machines, servers in locked rooms. Normal people didn't think about firmware measurements or cryptographic roots of trust. Then the rules moved upstream. Suddenly, an operating system update didn't just bring new features, it brought requirements, hardware requirements. A specific version of this chip, a specific configuration. Turn it on, set it correctly, or don't install at all. And millions of perfectly working computers failed the test. Not because they were slow, not because they were broken, but because the tiny chip said, "I don't recognize you." That's when users ran into the wall. People tried to dual boot. The chip objected. People replaced components. The chip forgot them. People recovered data from old drives. The chip refused to unlock them. Nothing was wrong. Everything was just unauthorized. Here's the uncomfortable math hiding underneath. Trust in this system is binary. Pass or fail. Known or unknown. Approved or rejected. There's no room for context. No appeals process. No explanation that says, "I know this looks different, but it's still me." And this power isn't theoretical. A manufacturer can decide which firmware versions are valid. An OS vendor can decide which configurations are acceptable. A platform can decide which keys are allowed to exist. All enforced by a chip that cannot be reasoned with and cannot be patched away. The irony is sharp. The more secure the system becomes, the more fragile it feels. One update goes wrong. One setting flips. One mismatch in measurements, and suddenly your own computer treats you like an intruder. Even recovery tools must ask permission. Even administrators are guests. And the humor, if you're looking for it, is quiet and dark. We built computers to follow instructions. Then we built instructions to follow computers. Now we argue with machines that respond with math. This is the moment the story stops being about hacking and starts being about ownership. Because when control moves this early in the boot process, it's no longer about software choice. It's about who gets to define valid. And once that definition is baked into silicon, changing your mind becomes expensive or impossible. The chip doesn't hate you. It doesn't favor corporations out of spite. It just enforces the rules it was given perfectly. The question is, who wrote those rules and why they're so hard to escape? This tiny chip isn't evil. It isn't a villain hiding on your motherboard, plotting against you. It's a tool, a very effective one. It stops real attacks. It prevents real theft. It raises the cost of compromise so high that most criminals don't bother. And that's the part everyone agrees on. The part that lingers is what quietly changed along the way. Security used to be something you added. Now it's something you're born into. Your computer arrives with assumptions already made about which software is legitimate, which updates are acceptable, which configurations count as safe. You don't negotiate with those assumptions. You inherit them, and inheritance is subtle. Most of the time, the chip works in your favor. Your disk unlocks automatically. Your system boots cleanly. You never think about it. That's the success case. Invisible, boring, efficient, until it isn't, until you want to run something different, until you want to fix something yourself, until you want to step outside the approved path. Then the tone changes. The system doesn't say no loudly, it just fails quietly. Features disappear, access vanishes, data becomes technically present and practically gone. And here's the risk that rarely makes it into product announcements. When trust is enforced by hardware, dissent looks like malfunction. A choice to experiment can look like an attack. A repair can look like tampering. A different idea can look like corruption. None of this requires bad intentions. It only requires alignment, or the lack of it. Right now, that power is mostly used for security and compatibility, but the mechanism doesn't care why it's used. It only cares that the rules exist and the signatures match. And once a system is designed this way, reversing it is not a software update. It's a philosophical decision. Do you want a computer that always protects you from unknown code, or a computer that lets you decide what unknown means? Because the tiny chip on your motherboard already made a partial decision on your behalf. It wakes up before you, it checks the world, and it decides whether the rest of your computer deserves to exist today. The unsettling question isn't whether this is good or bad. It's whether, in 10 years, you'll even notice when that decision changes. Done watching? If you like this video, hit subscribe for more cool stuff.